Hey, Ali, can you help me go over these linear algebra notes? I'm a little lost.
Yeah, totally. I was just looking at them. It's a bit dense, right? What do you think this first question means? How can we measure what a matrix does to space?
Right. I think it's leading us to the idea of rank. But before that, we need to review a couple of things first.
Okay, let's do it.
So, first up is Theorem 1. It says if V prime is a subspace of a vector space V, then the image of V prime under a linear map F is also a subspace of a different vector space W.
Wait, what's an image? Like a picture?
That's a great question, and this diagram helps a lot. It's not a picture like you'd take with a camera. Look at the left side of the diagram. We have a vector space V, and inside it is a smaller subspace V prime. When we apply the linear map, or function, f, to everything inside V prime, we get a new set of vectors on the right side, in the space W. The result of that transformation is what we call the image of V prime. The theorem says that this image, f of V prime, is also a subspace of W.
Oh, okay. So it's just what you get when you transform the entire subspace V prime with the function f.
Yep, exactly. And the theorem says the result is still a subspace. Okay, the next page defines the rank of a linear map. It's called rank F, and it's the dimension of the image of V under F. So rank F equals dimension F of V.
So the rank is just a number. What does that number tell us? What does dimension mean in this context?
It's the number of vectors in a basis for the image. Think of it as how big the transformed space is. And this next one, lemma 2, it connects the rank of a matrix to its column vectors. If you have an m by n matrix A with columns v1, v2, all the way up to vn, then the rank of A is the dimension of the subspace generated by those column vectors. That subspace is written as angle bracket v1, v2, all the way up to vn.
So the rank of a matrix is basically the number of linearly independent column vectors.
Exactly. It's the dimension of the column space. That makes sense. And this next one, Theorem 3, it just solidifies that idea. If a subspace V prime is generated by a set of vectors, then the image of that subspace is generated by the images of those same vectors.
Oh, that's pretty intuitive. You just apply the transformation to the basis factors, and that gives you the new transformed space.
Right. And it also says that the dimension of the original subspace is greater than or equal to the dimension of the transformed subspace.
Why is that always true? Does a linear transformation always shrink or keep the same size?
Not necessarily shrink, but it can collapse things, like a 3D space can be flattened into a 2D plane, or even a 1D line. The dimension can never increase, though. This next part, connecting matrices and linear maps, is where it all comes together. Definition 2 defines the linear map associated with a matrix F sub A. It says F sub A of V is just the matrix A multiplied by the vector V.
This is what we've been doing all along, right? Thinking of a matrix as a function that takes a vector and spits out a new one.
Pretty much. So Theorem 4 is what we've been leading up to. It states that the rank of the linear map F sub A is the same as the rank of the matrix A.
That feels like a relief. So all those concepts we just talked about, the rank of a linear map and the rank of a matrix, are basically the same thing.
Yep, and the proof on the next page shows why. It uses the fact that the image of the space is generated by the column vectors of the matrix. Since the rank of the map is the dimension of the image and the rank of the matrix is the dimension of the column space, and those two spaces are the same, their dimensions must also be the same.
Okay, so if the rank of a matrix is the dimension of the output space, where does the lost dimension go?
That's exactly what the notes ask. We know from Theorem 3 that the dimension of the output space, rank A, is less than or equal to the dimension of the input space, n. The difference, n minus rank A, is the loss dimension. The notes say the loss dimension is what we call nullity. This is where the concept of the kernel comes in. The kernel of a linear map F is the set of all vectors in the input space that get mapped to the zero vector in the output space. It's the set of all v such that f of v equals 0.
So it's all the vectors that collapse into the origin.
Yes, that's a good way to think about it. The dimension of the kernel is called the nullity. This brings us to the most important part of these notes, the Rank-Nullity Theorem. It states that the rank of a matrix A plus the dimension of the kernel of its associated linear map equals the number of columns in the matrix, n. So rank A plus dim ker f sub A equals n. The proof is pretty straightforward. To find the kernel, we need to solve the homogeneous equation AX equals 0. The set of all solutions to this equation is the kernel. When we find the reduced row echelon form of A, we find the rank of A as the number of the pivot columns. And the general solution for X is expressed as a linear combination of a set of vectors. The number of these vectors is equal to the number of non-pivot columns.
Wait, why are the non-pivot columns so important? How do they give us those vectors?
Great question. When we have the RREF, the variables that correspond to the non-pivot columns are called free variables. We can set these free variables to be any value, which we represent with parameters like C1, C2, and so on. Then we use the equations from the RREF to express the variables from the pivot columns in terms of those free variables.
Ah, I think I see. So the general solution is now written as a vector where each component is an expression involving the parameters.
Exactly. And we can then pull out those parameters to get a linear combination of vectors. The vectors that remain, one for each free variable, form a basis for the solution space. These vectors are special because of their structure. Look at the notes on page 14. The jth component of a vector u sub j is 1, since it corresponds to a free variable that we set to 1. The kth component of a vector u sub j is 0 if k corresponds to a different free variable. And the remaining components for the pivot variables are determined by the equations from the RREF. This structure ensures that the vectors are linearly independent. Since they span the kernel and are linearly independent, they form a basis for the kernel. Since the number of basis vectors is the same as the number of free variables, non-pivot columns, the dimension of the kernel is equal to the number of non-pivot columns.
Oh, so the non-pivot columns are literally telling us how big the kernel is.
Yep, the dimension of the kernel is n minus r, where n is the total number of columns and r is the number of pivot columns, which is the rank.
Oh, okay, so the dimension of the kernel is n minus rank A.
Right, and if you rearrange the equation, you get the Rank-Nullity Theorem. Rank A plus dimension the kernel of f sub A equals n. It's the lost dimension we were talking about. The rank and the nullity add up to the total dimension of the input space. Let's look at the example. We have a linear map f sub A from R5 to R4 determined by this matrix A. We need to find the basis and dimension of its kernel.
Okay, so the input dimension is n equals 5.
The first step is to find the reduced row echelon form of A. The notes show it has 3 pivot columns, so the rank of A is 3.
Okay, and the number of non-pivot columns is 5 minus 3, which is 2, so the dimension of the kernel should be 2.
Exactly. Step 2 is to solve AX equals 0. The variables corresponding to the non-pivot columns, the third and fifth columns, are our parameters, C1 and C2. The general solution is a linear combination of 2 vectors.
Ah, I see. Those two vectors are the basis for the kernel.
That's right. Step 4 confirms they're linearly independent, and step 5 states the dimension of the kernel is 2, and it checks out with the Rank-Nullity Theorem. 3 plus 2 equals 5.
Wow, that actually makes a lot more sense now. I get the intuition behind it. The rank tells us the size of the output space, and the dimension of the kernel tells us the size of the space that gets squashed to 0. Together, they have to equal the size of the original space.
Yeah, it's pretty neat how all the pieces fit together. Now I feel a lot better about the quiz on this.
Me too. Thanks for walking through it with me. I'm glad we didn't miss any of the details.
Anytime. Do you want to go grab a coffee?
Sounds good.